All right, today's lecture is going to focus on the nucleus and why we have radioactivity and why we have nuclear chemistry. Not all nuclei are stable, and we've already talked about atomic mass, that the atomic mass of an element is indicated by the isotopes that are naturally occurring. Um, Even if it's naturally occurring, some elements will naturally radioactively decay, and that's because the nucleus is an unstable one. All right. So this is why an atom needs to or will eject particles from its nucleus as a way to become more and more stable. And eventually, once a new stable nucleus is formed, then potentially the element will no longer decay. All right. So these nuclear reactions, as you see at the top, are reactions which involve a change in the nucleus. And therefore, most often in chemical reactions we're going to investigate this year, if I have carbon on the left side of a chemical reaction, it is a reactant. There's going to be carbon on the right side. The carbon atoms are not going to change. They might change who they're bonded with, but the amount of carbon on the left side will be equal to the number of carbon on the right side. But in these nuclear reactions, we might have carbon decay and become boron. And that's because the number of protons in the nucleus might change. And if that happens, then we are no longer talking about the element carbon, but actually boron. Now, we must still follow the law of conservation of mass. The mass of these reactions will still be conserved, so the total mass on the left side must always equal the mass on the right side. But now we're going to potentially see a change in the nucleus because, again, of stability reasons and issues. Radioactivity, a substance which simultaneously emits radiation. Any substances, element that emits radiation is called radioactive. The radiation that it does emit are the particles that it ejects, and these particles could be alpha particles, beta particles, could be gamma rays, all these different energy sources, which we'll talk about in today's lecture. And the reason why these things decay is because typically their neutron to proton ratio is not in the band of stability, which we'll talk about. If the ratio is a little bit out of whack, the nucleus is not stable and therefore it must decay to reach stability. The other reason is also mass. We get to a point that the mass of the nucleus is just so great that the strong nuclear force, one of the fundamental physical forces, just cannot hold the nucleus together. There's just too much mass and too many positive charged particles in the same tight spot that it can't stay together, and it therefore ejects particles to make it lighter and less massive. Okay? The substance that is released, that is called radiation. Okay? Now there's two basic types of radiation. There's radiation that is charged particles, that the nucleus releases particles that have a charge to them, and therefore in a magnetic field. For example, if I have a positive magnetic plate and a negative magnetic plate, if I send a particle through it, and that particle has got a negative charge to it, as it enters the magnetic field, it's going to be deflected upwards towards the positive plate. And that's because we find out that unlike charges attract. So, if the radiation source, when it's sent through a magnetic field, gets attracted or bent in a direction towards a positive or negative end, we now know that that is an ionizing source of radiation. And those are called alpha and beta. If the radiation source goes right through that magnetic plate and it's undeterred, then we know it's a non-charged source of radiation, and that would be examples of neutrons and gamma rays. Now, I did briefly talk about this band to do what they do. All right, so what are the particles that are ejected that you need to be aware of? The first is an alpha particle. An alpha particle, as you can see here, is a helium nucleus. It's got a mass of 4 AMU, and it has 2 protons. In essence, it is 2 protons and 2 neutrons. It is literally the nucleus of a helium atom. And therefore, all nuclei are charged because it contains protons and neutrons. So if I've got 2 protons, 2 neutrons, what's the charge on an alpha particle? And you should say +2. It's a positive energy source. It has a mass of 4 AMU. It is by far the largest particle that is emitted from a nucleus, and that's the purpose. Typically, elements that are too big, have too much mass, will emit alpha particles because they are just too large. while they're very massive, they tend to have very low penetration abilities. Your skin, for example, will block an alpha particle. Alpha particles cannot enter your body, and therefore they are usually harmless sources of radiation to your body. A beta particle is just like you can see, there's pretty much an electron. Okay, it's a particle that has a negative charge to it, -1, and the purpose of a beta particle is the fact that you'll see that it has an atomic number of -1. So when a beta particle is ejected, what literally happens is we decrease the number of protons in the nucleus. And this occurs whenever our proton ratio is too large, as we saw previously in the band of stability. It effectively has no mass because the upper part of the beta particle's got a 0 to it. And when you have a 0 to that, that's the mass number, and so it has 0 mass. So what really happens in a beta particle here is a proton gets converted into a neutron. Okay? Gamma radiation is just high energy. It has no charge and it has no mass. What it really is just a high energy source. It is the highest energy source that we'll review in nuclear reactions, and these particles can go through several feet of lead. Gamma radiations are the high energy particles that, if you're exposed to radiation, can cause damage to your bodies. You might seen radiation burns. They can also do damage to the point, prolonged damage like cancers and birth defects and things like that. They are very, very dangerous particles. Beta and neutrons tend to have a medium source radiation, where, again, a lead vest, if you go and get an x-ray, for example, done in a dentist's office, a beta and neutron emission can be blocked by those types of vests. However, they do penetrate body tissue, so they too can cause damage if you're exposed to them. Neutron, there is no Greek letter for it, so symbol for it, it's just a neutron, so I'm not going to put a Greek symbol down. This is the Greek symbol for alpha, beta, and gamma. All right, a neutron has 0 charge because it's a neutron, and it does have a mass of 1 AMU. Okay. Now, what we're going to investigate, start looking at, is how these nuclear reactions occur, and we're going to focus on is something called a nuclear decay reaction. The reactant, the substance that we begin a reaction with, is called the parent. So we're going to start with a parent isotope, which is unstable, and it's going to eject a particle from the nucleus, and when that particle is ejected, it's going to become a new isotope. That isotope is called the daughter. So the parent isotope gives birth to the daughter, and by ejecting the particle, the daughter has got a greater stability than the parent does. Now, the daughter might still be unstable and further undergo more decays, but compared to the parent, it is getting closer and closer to the band of stability. A couple things with these nuclear reactions is the sum of the atomic numbers must always be equal, and the mass must be conserved. We must still follow the law of conservation of mass. So the best way of doing these nuclear reactions is just to see an example of one. Okay, so for example, thorium-230. Now, whenever we do these reactions, we want to write them in nuclear symbol notation. So thorium is TH. So if you'll want to have your periodic table in front of you. You find TH. TH is a very heavy element. It's down in the very far bottom of the periodic table in that block that's pulled out. It's element number 90. So the atomic number of thorium is 90. And you'll notice in hyphen notation that the mass number is put out in front. So thorium-230 undergoes a decay, and we're told that it undergoes an alpha decay. So an alpha decay is a helium-4 nucleus. Now, by ejecting that particle from the nucleus, what forms from it? Well, the nice thing about this is nothing more than following the law of conservation of mass. The two particles on the right, their masses must add up to the parent. So if 4 AMUs get subtracted from the 230, what are we left with? 226. The atomic number goes from 90, it ejects 2 protons, leaving behind 88. We look up element number 88, and it's Ra, radium. So thorium, by ejecting an alpha particle, becomes radium. And usually what also gets ejected is alpha is gamma radiations as well, which lowers the energy of this particle, making it more stable. But this is something that you do not have to be aware of for the test. So on the test, what I'll do is exactly this problem shows. I'll say thorium-230 undergoes an alpha particle decay. What daughter isotope forms? And your answer would be radium-226. Okay? So this is what you must be able to do for this section of the test, or this unit, is be able to, key thing is to memorize the particles, or because you are at home, write those particles down and simply do a subtraction and figure out what particle forms from it. Now, if that radium-226, which is also too large, remember, if it isn't to bismuth, it's not stable yet. So now radium-226 undergoes a further decay by ejecting another alpha particle. What forms from it? Again, subtracting 226 minus 4, we get 222. 88 minus 2 is 86. And the element now becomes radon. Okay, so that's how we do alpha decays. The next one is a beta emission. So a beta emission, I wonder if I said that backwards on the previous page. And I did. It was the other way around, my fault. So a neutron gets converted into a proton under beta emission. So my apologies. And so when we have a beta particle, what's happening there is a neutron is being converted to a proton. So whenever we have too many neutrons, it would undergo a, and in your packet, now again, these lecture notes come from the packet. There's an why these elements. Okay, we have protractinium-234. So I find protractinium, Pa, on the periodic table, and it's got an atomic number of 91 and 234. It ejects a beta particle, which, as I said before, a beta particle is a 0, -1 particle. So the key thing is to memorize the formula of that particle. And if you do, then it's nothing more than subtraction. So now you'll notice that the mass number on the top is a 0. So we've done nothing to the mass. So it's still 234. But now what number must go here so that the two numbers on the right add up to the number on the left, which is 91? It can't be 90, because 90 plus -1 gives you 89. So it's 92. So 92 plus -1 add up to 91. So when we have a beta particle, what you have to remember is these are subtractions. So it's like saying 91 minus -1, which gives me 92, because when we subtract a negative, we add. So what happens is the atomic number goes up. And this is, again, because what happens is a proton gets converted into a neutron. Oh, excuse me, the other way around, my fault. A neutron gets converted into a proton. And that's why the atomic number does not change. Okay? And now I'm looking back in my lecture note emission. So if I get into the band of stability. Okay? All right. Go ahead and try to do sulfur 35 now, doing the same process. So pause the lecture now and see if you get the right answer. Picking back up, sulfur 35. We look up the atomic number of sulfur, and it's number 16. It ejects a beta particle, and it goes up from 16 to 17. And the element now is chlorine. Okay? So here we have the balance equation. Both sides, 0 plus 35 is 35. 17 plus -1 is 16. Our reaction is balanced. So this is, like I said before, actually a conversion of a neutron to a proton. And this will always occur when the neutron to proton ratio is too large. There's too many neutrons, and we have to convert a neutron into a proton by ejecting a beta particle. Okay? One other type of decay is a positron emission. Okay? In a positron emission, what happens is, this is what happens when the proton ratio is too small. We have too many, not enough neutrons to protons. So in a positron emission, it's exactly like we can already predict. So oxygen 14. The atomic number of oxygen is 8. So in a positron, it's a positive electron in essence. It's a positive electron particle. So now when I subtract across, 14 minus 0 gives me 14. 8 minus 1 gives me 7. The oxygen now becomes nitrogen. So a beta particle is a positive electron. Again, you'll notice that the mass doesn't change because neutrons and protons effectively have the same mass. But this is happening because a proton is being converted to a neutron. And how is that possible? If I'm able to remove the positive charge off of a proton, what I'm left with is just mass and effectively a neutron. And that is, in essence, a beta particle. Okay? It's not a beta particle, a positron particle. So positron, think positive. Beta, think negative. But both a beta particle and a positron particle, the mass number, the top number is 0 because, again, neutrons and protons are being converted into each other, and therefore the mass doesn't change. The only one that changes the mass of the nucleus is an alpha decay. Okay? And as I said before, a gamma radiation source, all we're going to see is effectively is energy is released. We are not going to change a particle. So for example, if I have nitrogen 14.7, if we're to undergo a beta, if we're to undergo a gamma radiation emission, let's say the particle is just too energetic, it'll emit a beta particle, but the isotope still stays the same. So whenever there is a gamma radiation source, it's because the isotope itself is too energetic and it just simply sheds energy in order to become less energetic. But again, when we emit a gamma radiation source, it does not change both the top and bottom numbers. All right, so quickly, just for additional practice, what I'd like you to do is stop the lecture now and try to do the following 3, 4, 7 examples. And then when you're done, please pick back up with the lecture and see and check your answers. So I'm going to pause lecture now, complete the answers, and then when you start the lecture again, these answers will pop up on the screen. All right, so I've placed the answers to the practice problems up here so you can take a quick look and you can see, again, whenever we have an alpha particle emission, we are simply going to subtract 4 off of the mass number and 2 off the atomic number, and we effectively are reducing both the mass and number of protons in the nucleus. And again, the goal here is to get the daughter isotopes to become lighter and lighter, getting closer and closer to bismuth so that we reach a stable nuclei. In a beta particle, again, we have, too many neutrons. So again, a neutron is being converted to a proton, and therefore we see the atomic number getting larger by 1. And then in the positron particle, we have a proton being converted to a neutron, and now the atomic number is decreasing, but both the bottom two, beta decay and positron decays, are both keeping the same mass number. So what you have to be able to do on the test is be able to complete these nuclear reactions. And again, keep it simple. All you've got to do is make sure that with the arrow, treat the arrow as an equal sign. The numbers on the top, on the right side of the arrow, those two numbers have to add up to the original mass of the parent that starts the reaction. And the atomic numbers on the bottom, you need to add those up, and they must equal the original atomic number for the original isotope as well. And if they do, you have followed the law of conservation of mass. And again, the other big key thing is to be able to memorize the 3 particles. You're going to be expected to be able to do either an alpha decay, a beta decay, or a positron decay. So keeping those particles straight, and when you see on the test this isotope undergoes an alpha decay, immediately you know what particle on the right is being ejected, and then it just becomes simple mathematics. And that's how you do nuclear decay reactions. So now, after completing this lecture, I've got a worksheet online that goes over some of these key concepts that I'd like you to go through, fill it, and complete, and then check over with the answer key. Again, thanks for listening. If you have any questions, please do not hesitate in contacting me. Thanks again. Trying to copy that you have. But in that packet, you see what's called the band of stability. And all these little blips and blurps on here are actual isotopes of stable nuclei, all the way down from elements that are very small, okay, hydrogen, all the way up to the largest element, which is bismuth, which is this one right here. Bismuth is the last known chemical is the last known element that possesses a stable nuclei. Any element beyond bismuth is radioactive, and therefore it is not stable. Now it might take hours, years, months to decay, but it's still not a stable source. So once we get beyond bismuth, the atom is just too big, and the nucleus just cannot stay together forever. It's an unstable element. Okay? You'll notice this dark line is a 1-to-1 ratio of protons and neutrons. And early on, you'll notice that the elements fall pretty close to a 1-to-1 ratio of protons and neutrons. But as we start getting to heavier and heavier elements, the band of stability starts falling closer to a ratio of 1 proton to every 1.5 neutron. So we end up getting more and more neutrons per proton in order for there to be enough distance between positive charges so that there isn't so much repulsion between those. So we're going to investigate this band of stability. Any isotopes, if we were to plot this, and that's going to be our activity for this week, if you were to plot an isotope and it were to exist over here, it is outside the band of stability, and therefore this atom would be radioactive. And it's because if you look at this graph, atomic number is number of protons, and this is neutrons. If I have a particle, an isotope that exists here on this band of stability graph, what is wrong with it? Does it have too many protons or too many neutrons? And hopefully looking at this graph, you determine that the number of neutrons is too large. And therefore, we have to do some type of radiation or radioactive emission to try to drop that particle down or over so that it gets into the band of stability. So based on knowing where we are in conjunction to the band of stability, we can start to predict what type of radiation sources that isotope may emit. If the particle exists on the other side of the band of stability, now the number of protons is too large, and we have to go ahead and cause it to decay in such a way that will cause it to get into the band of stability. And some of these elements might undergo multiple ejections of particles until they get to a isotope that is within the band of stability, and then it will stop emitting radiation. Okay? So fundamentally, that's the go back to the band of stability. So whenever I'd have an isotope on the left side of the band of stability, anywhere over here, this would be, we would predict that it would undergo a beta decay because we have too many neutrons. And we need to convert neutrons into protons so that it will